Thanks, John, for the introduction. Thank the audience for your time today. I know we're all busy and we have lots of meetings, and I appreciate you guys carving out a little bit of time for me to talk about the research we recently presented at the AAPS meeting. So this was, part of our attendance at the recent AAPS Farm Sci 360 meeting, which was virtual. SMS has a long history of the AAPS meeting. We've been there since 1998. We presented or collaborated on over 60 posters. This is just a back of the envelope calculation. We typically collaborate with other universities, industrial partners, or research institutes. And this helps us be at the forefront of physical characterization of pharmaceutical materials for well over 20 years. We recently put together a history of all our posters that we have presented at the AAPS meeting from 1999 to 2020. This is just a small little snapshot. If you would like a complete list of the posters with the abstracts, and then if you want to request an actual copy of the poster or further information, you can contact us at science@surfacemeasurementsystems.com. So part of the reason that we are presenting at AAPS, and we're always trying to push the boundaries of what our instrumentation can do, both hardware, software, and application space. These are just some of the milestones that SMS has pioneered over the years. First and foremost, being the first commercial DVS system, and several other generations of the DVS and inverse gas chromatography instrumentation. So enough of the sales pitch. I will get to the science portion of this presentation. And as I mentioned, this was one of the posters that I'm going to focus on today that we presented. SMS was part of two other posters. Another one with a collaboration of the Imperial College London and Takeda Pharmaceuticals that had to do with humidity degradation of APIs using DVS and in situ Raman. And one we did with DuPont looking at permeation absorption of water and ethanol mixtures in ethyl cellulose films. Again, if you would like copies of these posters that were presented at the APS meeting, we can just email us, science@surfacemeasurementsystems.com, and we'd be happy to provide them for you. So getting on to today's topic, myself and our partners were interested in looking at glycine. One of the reasons is glycine is a naturally occurring amino acid. It does have significance in a broader sense in biological materials, as it is a building block for molecules like peptides, proteins, and precursors for a lot of different applications. So we thought, since this was a fundamental and relatively simple compound, studying the interactions of these would become important for broader studies. So just to give the molecular structure of glycine and its oligomers, we wanted to look at glycine, and then we wanted to look at diglycine, triglycine, tetraglycine, and pentaglycine. So we wanted to see, as the glycine chain got longer and longer, how that would affect the surface properties and the wettability of these materials. In order to do that, we used the main things we were looking at were the surface energy values. This was done by the inverse gas chromatography. These measurements were done at infinite dilution at 30 degrees C, and then we wanted to look at the effect of relative humidity on these properties. So we measured the surface energetics at 0, 10, 30, and 50% RH. As a complementary technique, since we were interested in the effects of humidity and the phenomena that we observed, we wanted to correlate with the water absorption studies. So we did some DVS, dynamic vapor absorption, at 25 degrees C, looking at moisture on and moisture off. To more further understand the why between the observations that we saw, we did some modeling work, and I will freely admit that I am not, a theoretical modeling person. So the details of the different models and things that were used are here. If any customers or any attendees have any specific questions, I'd be happy to get that information for you, and we can get in touch. And I failed to mention, I'll go back, and my apologies to the co-authors on this, in particular, Vikram Kardi at London Imperial College, who did the inverse gas chromatography and some of the vapor absorption work. Ian Rossbottom at Imperial College did the modeling work, and Frank Thielman, who was a consultant on this project. So if you have specific questions about the modeling, we'd be happy to get you in contact with Ian. And this study that I'm showing today is in the progress of writing up as a journal article. And once that's accepted, we will be releasing that article to the public. So my one slide, I'm not going to go into what inverse gas chromatography is, but basically it's a gas-phase technique, and the molecule or the material is put into a column. We pass a series of gases or vapors over that material to measure the retention time, which is related to things like surface energy. So inverse GC is a common way to measure the surface energy of fibers, powders, particulates, granules. It's analogous to surface tension of a liquid. It's directly related to the thermodynamic work of adhesion, and it's very often divided into a dispersive and an acid-base component. So this gamma is the surface energy, the T is for total, and that's often divided into a dispersive and an acid-base contribution. And that's what we did with this particular set of samples. We measured the surface energy. So in the red and white checker bars, this is the dispersive, which is a measure of the nonpolar, or also sometimes called gamma LW for London van der Waals. And the blue checks are the acid-base component of the surface energy. So this is the data for glycine. So this is just the simplest glycine. And you can see here, when we go from 0 to 10 to 30 to 50% relative humidity, we see no measurable change in either the dispersive or the acid-base surface energy. So number one, for this particular material, the very little effect on relative humidity, and the polar contribution is relatively small compared to the dispersive contribution. So we can see here that the acid-base or polar contribution to surface energy is a fraction of the total surface energy. So this was for glycine. Now we move to triglycine, and you can see here a couple things. Number one, there are some error bars here on some of these measurements, so there were some repeat on some of the runs to give you an idea of the sensitivity of the measurements. Number two, if we just look at 0% relative humidity and we compare that to glycine, we can see an increase in the acid-base contribution as we increase the chain of the glycine molecule. So we can see here that the acid-base contribution is much higher. Number two, we can see is as we go from 10 to 30 to 50% relative humidity, we do see that the molecule is now sensitive to moisture, and we see a change in the surface properties as we go from the dry to the partially hydrated state. And this trend continues as we increase the chain in the glycine molecule. So here is tetraglycine, and again, we can see that as we increase this glycine chain, we can see an increase in the acid-base contribution. We see that goes much higher, and we see that the material is sensitive to moisture. As again, we go up in relative humidity, we're seeing a decrease in the surface energy, and the surface properties change as the material becomes hydrated. And that trend continues even further as we go up to pentaglycine. Again, we see that we go from tetraglycine to pentaglycine. The acid-base contribution to the surface energy increases further, and we see an even stronger dependence on relative humidity. And we can see, again, a stronger dependence on relative humidity. As we go to more humid conditions, the surface properties change. So just to summarize, if we only look at the data at 0% relative humidity, and we can plot the excuse me, acid-base contribution to the surface energy, we can see a very distinct increase in the acid-base portion of the surface energy as we increase the glycine molecule chain, and we can see an increase in basically the polar peptide bond. So as we go from glycine to diglycine to tri to tetra to penta, we see a very strong dependence and increase in the acid-base contribution of the surface energy. So we saw from the inverse gas chromatography results that the molecules, as we went up the glycine chain, became more and more sensitive to moisture. So we wanted to investigate that a bit further. So we did some dynamic vapor adsorption, which most of you in the audience are probably familiar with. Basically, the instrument delivers a relative humidity flow of air to the material, and a microbalance measures the mass change as a function of relative humidity. So a sample graph here is showing for triglycine, and you can see the red line is the sample weight as a function of time. The blue line is the relative humidity as a function of time. So as you increase the relative humidity, the sample picks up weight. As you decrease, the sample loses weight. In general, this triglycine, I'll show a summary in a few slides, is relatively hydrophobic. We see only a 0.06, 0.05% weight change. So although it does pick up moisture, it is relatively hydrophobic. As we go up in glycine chain length and we go to tetraglycine, we can see we go from less than 0.1% uptake to a 0.6% uptake for tetraglycine. And pentaglycine, we see an even larger change, over 2.5 weight percent as we, or over 2% weight change as we go to tetraglycine. And to summarize, excuse me, this data here, this is only showing the maximum uptake. So the maximum sample weight at 90% relative humidity. We can see as we go from glycine to glyglycine to triglycine to tetraglycine to pentaglycine, we can see it goes up. So the material becomes more hydrophilic as we increase the chain of these glycine molecules. And we can see a rather large jump as we go from tetraglycine to pentaglycine. If you go back again to here, this is less than only about a 0.5% change to well over a 2% change in mass. So we can see we would expect this trend to continue as we go up in chain length. In order to get a more fundamental understanding of why this is occurring and how water is interacting with the materials, we did some modeling of how moisture interacts with these materials. And again, if you want specific details on the assumptions and the types of models used, I'll be happy to provide that information offline. Just send me an email. So we are not finished all of the modeling results, but we have done it for some of the lower chain glycine molecules, and this is for diglycine. And what the modeling suggests is that the dominant 100 face is more less hydrophilic or more hydrophobic than the side faces. So the predominant crystal faces that are going to be arrangement, the dominant surface is going to be hydrophobic, whereas the less dominant surfaces are more hydrophilic. And there's less interactions in this tightly packed space. So this diglycine becomes very tightly packed, so it's hard for water molecules to get in there and interact with the material. As we increase to triglycine, It's actually suggests that the 0-1-0 facet is more dominant in the packing arrangement, and this is a more hydrophilic. So the large 1-0-0 side is more hydrophilic, and this is also showing that that these needle-like things will lay flat and allow for more ability or mobility and more space for moisture to get in and interact with the sample. So the again, we are in process of doing the tetraglycine and the pentaglycine. Those are currently being done by Ian. But the initial modeling results suggest that the increasing rugosity and basically mobility or spaces in the material and allow for more hydrogen bonding sites, and the major habit faces of the increasing chain length glycine changes from when you go to a simple glycine molecule to when you increase the chain length. The dominant habit that is faces the outside of the structure changes, and this makes the surfaces more attractive to water, and this is also correlated to the significant changes in the surface energies and the moisture absorption results as we go to the longer chain length oligomers of glycine. So as I mentioned, the tetra and pentaglycine are undergoing modeling currently, and we will have those results in the final paper once it's complete. So in conclusion of this relatively quick overview, we saw an increase in the acid-base portion of the surface energy as we increase the oligomer to longer chains. This is due to the polar peptide bonds in the glycine. The longer chain glycine oligomers, in particular pentaglycine, showed a higher sensitivity to moisture, which showed a higher affinity for water. And it suggests that the additive nature of these free energies with the polar functionalities are there as we progressively increase the chain length of the oligomer. And the initial modeling on the molecular level suggests the possibility of some conformational changes in these molecules, which will affect how they interact with the moisture or water molecules in the environment. So as I wrap up, I'd like to thank again the collaborators, both at Surface Measurement Systems, and Armando and David helped with the other study, the Raman study, which I didn't talk about today, and also the ethyl cellulose film study. But in particular, I want to thank Jerry Hang, Vikram Kardi, and Ian Rossbottom at London Imperial College, Frank Thielman at Takeda, and most importantly, thank you for your time and attention and carving out a little bit of your day to listen to me talk about the research we recently did. And at this point, I can pause and open the floor to John to field any questions.
Thank you very much again, Daniel. That was a great presentation. As Daniel said, we would like to now open the floor to for anyone to submit any questions. So if you look to your right, you can see your questions panel. And we invite anyone to have it to post any queries they have from either today's presentation or from Daniel's presentation at the AAPS event. So we'll give you all a few moments just to submit any questions you have there.
Okay, I see a question about how you control the relative humidity in the inverse GC. Basically, that's done, there's a carrier gas, either nitrogen or helium, that constantly flows across the sample. And then we have the ability to pre-humidify that to distinct levels. So it's a constant background of 0, 10, 50, 80% relative humidity. So we expose the sample to a relative humidity. We keep it at that relative humidity. And in our system, we use a flame ionization detector. So the detector that's blind to water, so we can change the background RH, and we don't see any change in our chromatograph, the background signal, and then we can inject the organic molecules on top of that. So it's basically very similar to the DVS instrument, where we mix a wet and a dry flow to different proportions to deliver the requested relative humidity, and that is kept constant during the experiment. Is there another question that I see here? Okay, so I see, do you observe differentiable dispersive surface energy values between the glycines that you can correlate back to the major crystal facet for each glycine? That's a great question, and that's part of our ongoing, we want to finish the modeling on the larger chain glycines. Now, we do see some trends in the dispersive. I focus more on the acid base because that was very clear and direct. There is some indications that the dispersive energies are different, but we haven't finished the modeling quite yet. So we want to wait till we get a full picture before I make any conclusions on that. But it's a good question, and that's what we would like to finish up with the modeling of the larger glycines. So thank you for the question.
Daniel, we have
Okay.
a question submitted. Oh, sorry, you go ahead. You go ahead.
Yeah, so I do see that question, and the question was decreasing surface energy with increasing relative humidity is due to occupying high energy sites with molecules. Yes, you are correct. That is one explanation for that. However, we did not see that with the just the glycine by itself. So if we maybe go back and we looked at this very carefully to see if that was the only effect. If it was only due to moisture absorption occupying energy sites, we see basically no decrease in just here in with relative humidity, whereas the other glycines we do see that. So I'm not ruling that out completely. Yes, as you increase water, you're covering more and more of the surface with water molecules, and therefore you could see a decrease. But we think it's related to other things as well, not simply just occlusion of sites. Otherwise, you would see it across the board. So if the material is hydrophobic, you can see there's relatively no decrease. But as we increase the hydrophilicity of the material, we see that trend get more and more exacerbated as the surface is more and more hydrophilic. So yes, it is just due to blocking sites, but it also, the more hydrophilic the surface is, we do think there's fundamental changes to the surface properties, not just blocking sites. But it's a great question. We haven't looked at other orthogonal techniques like powder cohesion or how these materials behave with other either solids or vessels or anything like that. We haven't looked at that or done any other type of flow measurements or anything else to see how the knock-on effect might be. But we do think there is something fundamental with the reaction to relative humidity. Have I missed any other questions, John? I apologize. The screen's a little bit hard for me to see. But,
No, that's no problem. We have one here from Majid Fawaz. He says, what kind of applications are these molecules used in?
Directly, this molecule probably not as commercially interesting. We chose it is because it is a relatively simple molecule, and it is a precursor to other enzymes or proteins or things like that. So from a commercial standpoint or a therapeutic standpoint, I'm not sure what glycines themselves would be used for, but it is something that we could use that's a relatively simple and over the and you can order it from Sigma Aldrich, and it is something that could be as a building block for larger biomolecules. So that's why we chose it. It may not be directly related to a therapeutic effect, but it does show what we wanted to do is to see if structure was related to these properties that we can measure.
Great. We have a question from Stephen Anderson, and he's
Yep.
asked, was the purity of your glycine oligomers very high, and by that he means equal to or above 99.5%, to minimize the effects of impurities?
That's a good question. I don't remember off the top of my head on the purity of the glycines. I can get that information, but we did. These were kind of just I believe from Sigma. I didn't run the samples. These were done by Vikram in the Imperial College. I'll have to get more details on the levels of impurities, because that is an issue with any type of measurement, especially inverse GC, which would be sensitive to impurities. But I don't off the top of my head remember the purity, and I apologize for that.
Oh, that's fine. I'm sure it's something we can follow up with after, isn't it?
Yep.
A question from Stefanos Exnanda. Apologies for if I mispronounce that. Are there any differences in surface energy heterogeneity between each glycine?
That's a good question. We did not look at that at this point in the study. We just fixated or focused on the infinite dilution results, and that could be the next level that we look at, is the heterogeneity. So for those of you familiar with inverse gas with our IGC SEA, it is possible to not only look at infinite dilution, but out into the finite dilution, and not a single value for surface energy, but a surface energy heterogeneity. We haven't looked at that yet. We focused on this on the initial studies to just look at infinite dilution. But you're absolutely right. That could prove interesting, and also give some more a broader window into maybe are these different facets playing different roles as we go to different glycine chain lengths, and the heterogeneity could give some information on that. But we have not looked at that yet.
Great, thank you. A question from Rodolfo Pinal. He has asked, as you enlarge the number of monomers to a polymer, will it stop being crystalline? Do you have a sense of what may happen then?
Unfortunately, I don't have a sense, but you're right. I mean, at some point, you could fundamentally change, and I would imagine at some point you're going to get kind of a plateau effect, where predominantly the let's say the ends of the chain will be less important than the bulk of the chain, and you might not get to highly crystalline or structured packing. It could be very different, and that's a good point. But I don't know where that transition or where that cutoff would be. How many chain lengths do you have to go to get to that point?
Okay, and I think we have one last question from Duohai Pan. Have you done any amorphous material for the wettability measurement by DVS?
Sure, we've done lots of amorphous materials, whether it be spray dried materials, freeze dried materials, milled materials, and we have a pretty extensive history and understanding and publications looking at moisture absorption on amorphous materials. With low molecular weight amorphous materials, very often you can get a moisture-induced transformation into the crystalline phase, like a spray-dried lactose or a spray-dried salbutamol sulfate or some other smaller molecules. When they are exposed to high enough moisture, it can cause them to relax to the crystalline state. For larger molecules like proteins and enzymes and peptides, you typically don't get that, just because they can accommodate the moisture without relaxing, and they're more complex. But we certainly have a pretty broad and extensive use of moisture absorption with amorphous materials.
Great, fantastic. Well, I think that's all the questions we have for today. So thank you once again, Daniel, for giving that presentation. It was really informative. And thank you as also to our audience for posing some really great questions to our speaker. Daniel, do you have any last comments for our audience?
No, I just wanted to reiterate that please contact our science at Surface Measurement Systems if you have any further questions or want some more details. We'd be happy to answer those questions offline. And I just thanks for your time. We're all busy and we get webinar fatigue, so I appreciate you guys giving some time to listen to me talk today.
Yes, and I think everyone would join me again in thanking you for taking the time to share your findings with us today, Daniel. Just for our audience, for our next session, we've 2 weeks until our next session, so a bit of a break. But our next topic will be vapor pressure measurement of solids, oils, and liquids, and that will be presented by our very own Dr. Vladimir Martis. And you can find out more about that at www.surfacemeasurementsystems.com. Just as Dr. Burnett said, if you have any further technical queries following this session, please feel free to email us at science@surfacemeasurementsystems.com, and we'll get back to you as soon as possible. Thank you all again very much for joining us today, and I hope wherever you are, you have an enjoyable morning, afternoon, or evening. Thank you.